Well, Adam, thank you so much for joining me today. And on behalf of Soft and Way, I just want to thank you so much for taking some time to talk about your and your students' experience with AxSTREAM and with Turbopump development in general. And I just want to start a little bit about yourself. Tell me a little bit about yourself, how you got to the position that you are in with Launch Canada.
Yeah, absolutely, and thanks so much for having me. So I wear a number of different hats actually. By day, I am a turbo machinery designer at Pratt and Whitney Canada, so that's kind of my bread and butter. But in my spare time, for a number of years, I design, build, and test liquid rocket engines. And over the last 12 years or so, there has been this huge surge of interest in rocketry around the world, really, but particularly in Canada among university students. And I think, a certain amount of that is probably the SpaceX effect, where there's a lot of really cool work going on all over the world in that space. And for today's generation of students, it's really been inspiring them and motivating them to pursue engineering. In Canada, we've always kind of had this catch-22 because the whole launch and rocket propulsion piece has not historically been a major area of focus for us, but that's been starting to change, and a certain amount of that has actually been driven by these student rocket teams that have become almost this grassroots movement of sorts nationwide. And initially, I found myself mentoring a number of these individual student teams and helping teach them how to not blow themselves up when building rocket engines. Kind of as somebody who built up this skill set that was not really common here, so I wanted to pay it forward and do what I could to support the growth of this community. And things have really taken off, I guess, figuratively and literally across the country. And we now have something around 30 major university and college rocket teams, coast to coast, representing like well over 1,500 actively involved students. And a lot of these teams are doing really impressive work. One of our teams fired the largest student built liquid rocket engine ever developed. We've got students doing really impressive stuff. We now have a number of startup companies across the country, every one of which was either founded by former members of these teams or else hires almost exclusively from them. So it's really this entire new ecosystem that's been developing here. And a lot of that has been heavily linked to all of this student enthusiasm for rocketry. So after a number of years of trying to do what I could individually to mentor some of these teams, I was just hitting up against the limits of what I could physically do as one person in my spare time. So I started Launch Canada as a nonprofit back in 2019 to try to do this in a more organized way. And up until that point, these Canadian teams basically all had to travel to the U.S. to be able to launch their rockets. And there was a big competition there, the Spaceport America Cup, that was one of the real catalysts that enabled those teams to get started. And so part of what we really wanted to do was create a Canadian version of that competition so that they would have an event here where they could do these things and hopefully make it a lot more visible to industry in Canada as well, and try to elevate the profile of it. So that was kind of where Launch Canada came from. And we actually just wrapped up our third annual competition back in August. It was our largest ever, and we held that in Timmins, which is about 7 hours north of Toronto. And in addition to the competition, we've really been trying to take a broad approach to what we do to support these student teams. The competition stuff is great, but we've also found there's sometimes a real benefit to creating more collaborative projects that allow students from multiple teams to come together and work together with experienced industry folks like myself on challenging projects that might be bigger than any one of them could have easily done on their own. And so we call these our special projects. And our current signature special project is we're trying to develop the first rocket engine turbopump in Canada, and what also might be the smallest one ever built. And this is actually an offshoot of our first special project we held in 2021, which was basically a hands-on liquid rocket testing boot camp that took place over the summer. And I happen to have my own mobile liquid rocket engine test trailer, as one does. And so we kind of used that as a way to get the students involved in learning about how do you set up and test rocket engines, how do you develop instrumentation for it, what are the kind of safety practices you want to follow. And the whole goal of it really was to demonstrate a more professional approach to this and showcase, how would you actually do this if you weren't trying to just build the Home Depot rocket, but wanted to do this for real. And what kind of components would you want to use? What are the tools that you would probably want to take advantage of? And it was wildly successful. We had an amazing 30-second hot fire of 1,000-pound thrust liquid oxygen kerosene engine that worked perfectly on the very first attempt. So, like, how often does that ever happen? And I think the students all got a lot out of it and wanted more of it. So when we were looking at what the sequel to that might be, obviously as a turbo machinery designer myself, who also loves rockets, the holy grail project was always to try to do a turbo pump. So we figured, let's see if we can actually pull that off, and let's see if we can size it for this existing proven liquid rocket engine we had, which is a massive challenge in its own right, because this is much smaller than what you would normally see a turbopump used for. But we figured we would embrace the challenge and see if we could pull it off. And one of the real catalysts that convinced me that this wasn't totally insane to contemplate doing was actually Softenway's support with the AxSTREAM platform. So that was really one of the fundamental enablers for what we're trying to do.
Yeah, and that's a great segue. That was going to be my next question, essentially, is how you came to kind of start using AxStream and got involved with Softenway. I guess what was that process like, and did you guys try out multiple softwares? What was that like for you guys?
I'd actually met some of Softenway's people over a couple years at various space conferences and things, and we got talking about some of the stuff that we were doing here with Launch Canada, trying to build this talent to seed the industry. And I was already kind of contemplating where we could take this. And I was really impressed with AxStream and the potential that it offered, and especially as a turbo machinery designer myself, having that single platform that integrates pretty much end to end everything you want to do when developing and analyzing turbo machinery. Seemed like it would be a phenomenal benefit to make that available to the students, because this is a pretty specialized corner of engineering. And even when a university might have some sort of an aerospace propulsion course, usually it's going to be focused a lot more on like the thermodynamic cycles and that side. It's very rare to see anything get deeper into the actual mechanical design of these systems. And so seeing that AxStream existed as this complete integrated platform was pretty compelling. And so we got talking about some of these things that I wanted to be able to do. And Softenway really stepped up and made the platform available to our students. And so that's really been a part of the journey of this project from before day one.
In terms of just resources and education for the software, I guess what has it been like, kind of seeing students learn how to use it? Like you said, it's an integrated software. There's
Yeah.
you can utilize generative design. There's a lot of different tools in it. I guess what is it like, seeing students and kind of your role in helping them utilize the software?
Yeah, so I think one of the things that's been maybe a little bit unique with our particular project is, obviously developing turbo machinery is a very complex systems engineering project fundamentally, right? And they're not the kind of thing that you can just do over the course of a few months. Um, and so, with a lot of student teams, when they want to get into something like a turbo pump, it's not always easy to do something like that within the scope of a 1 year project. To say nothing of the cost that can be involved in actually producing hardware. And so, part of what we were really trying to do with this was get a little bit of guidance from folks like myself who do kind of have that end-to-end turbo machinery design experience so that we could demystify this a little bit and break the project down into more bite-sized chunks so they don't get too overwhelmed. So that was sort of a big part of it, and fortunately, Soft and Way had a lot of great resources that we were able to use from their online Turbo Machinery University. Um, Office hours with some of their engineers were a big benefit as well. And we also actually took a course that was generously provided by at a discount by the AIAA in the basics of turbo pump design, and that was a course that was developed with Soft and Way, and so it was a really nice way to kind of marry the theoretical side of the basics of how turbo pumps operate and how you design them with the specific tool that we were actually using. So we had a bunch of students take that course as well, which was a huge help.
If you could kind of let us know just where you are with the development of the turbo pump right now, I guess what that process has been like, and
Yeah.
also where, just maybe for a layman that's watching right now, I guess what the real world applications might look like in terms of using it in rocket engines.
Okay, yeah. So to the first part of that, where we're at now, we've been taking a very kind of incremental approach to doing this, and I know enough to know what I don't know, and so knowing what these developments typically look like, we wanted to give ourselves every opportunity to build experience and knowledge step by step. And so step one of the project was actually kind of a learning phase. So we had AxSTREAM, we had these other resources, we had textbooks and old NASA papers and all that kind of thing. And so we were able to get the team a little bit up to speed in some of the basics. Um, then we got into the actual development of our actual pumps, and we're doing this really in three major steps. So we're starting with an electric motor driven fuel pump. Our fuel is kerosene, so it's room temperature liquid. It's not terribly complicated to work with. The follow on to that is going to be an electric motor driven liquid oxygen pump. And we've deliberately tried to front load a lot of the design with our kerosene pump, and use it as basically like our workhorse test bed. So we're using it to try out some of the design concepts that we're planning on implementing with the LOX pump, not because we actually require that for a kerosene pump, but because we want to maximize the opportunity to learn with the easier fluid and then move forward to the more challenging one. So we've largely completed the detailed design of the electric fuel pump. We've got a lot of our major system components in hand already, instrumentation, all of that. We've got many of the major components either entering production now or going into production over the next month or so. So we're hoping that by fairly early in the new year, we will be close to being able to actually run our first pump, and then of course we'll get to see how close we came to AxSTREAM's predictions with this. The other piece that's been sort of the key enabler is we've got a number of manufacturing sponsors who are helping us actually turn this into real hardware. And one of our big ones is EOS, who are a leader in metal additive manufacturing. And so this combination of AxSTREAM plus additive manufacturing has been, an amazing opportunity for us to make real hardware. And it also allows us to try out a couple different concepts simultaneously. So we can print our top 3 impeller designs, for example, and then actually test them out and see how they function in the real world. So that's kind of the focus right now. And as we get into the more of the build and test side for the fuel pump, on the design side, we're going to be ramping up the design and analysis for our liquid oxygen pump. And we completed the conceptual design of our LOX impeller and inducer, thanks to AxSTREAM. So now we're going to be looking at what's going to be more or less common with the fuel pump, what's going to have to change, and of course, how we go and analyze the thermal gradients and all that piece that comes in when you start dealing with a cryogenic liquid. So that's kind of ramping up this year. And then the third phase of this is going to be integrating our pumps with a gas generator and gas turbine to make a full-on turbo pump. And we've actually been supporting some university capstone projects that are feeding into that one. We've got a capstone team from the University of Toronto who are working on design of a gas generator for our future turbo pump. So they're getting up to speed on how you do that piece, and it's a great little project for them because it's basically its own little fuel-rich rocket engine that they get to develop. And with our support from EOS, we can have little prototypes of that 3D printed and start building that experience. So probably 2026 is going to be where we actually get the turbo pump itself up and running, but we've got some sub projects that feed into that are underway right now.
And something I'm curious about is, obviously you being a turbo machinery developer yourself, seeing all these students being able to participate in something like this, have increased opportunities, in large part to you. I guess how have you seen them and their perspective on turbo machinery development change, throughout this process? I guess what
Yeah.
has that been like for you?
It's honestly been really cool to watch because I think, like with so many things, something can seem impossible or out of reach until suddenly it isn't. And for a long time, building a liquid rocket engine was the absolute pinnacle of student rocket projects that very few even bothered to attempt. But then that started changing. And what changes it is usually when the first one actually does it and shows that they can. And once you see that something is possible, you can't unsee that, right? And so that empowers others to start imagining themselves doing something that maybe they never thought they could. And after a couple years of that, you do see this really cool feedback dynamic happening where they just keep pushing each other to move to bigger and bigger things. And the ultimate frontier on the propulsion side obviously is turbo pumps. It's much harder to do than something like just a liquid rocket thrust chamber because with the thrust chamber you can kind of muddle your way through and get something that's going to work even if it doesn't work well. Whereas a marginal turbo pump is going to either destroy itself immediately or provide effectively no useful pressure and flow. And so it demands a real high level of excellence in how you approach it. But as you've probably seen, I know Softenway has been supporting a couple of student turbopump projects across Canada, and this is sort of a side effect of that, right? We've gotten more people who no longer think that this is something that's out of reach for them, and the more people we have who are willing to try that out, the better. One of the big things that I've tried to do with the Launch Canada project is, of course, make sure that the students are learning lessons that they can then carry back to their own teams and incorporate into their own projects. And one of the particular areas that I think I've been able to bring some value to is looking at that big picture mechanical design of the entire machine, because it is easy for a student turbopump project to like get hyper fixated on the impeller and inducer and volutes, without actually thinking too much about how that fits into the overall machine. So like rotor dynamics, what's that? Unfortunately, you kind of have to be factoring all of this in from the very beginning. And so this is one of those capabilities that AxSTREAM has offered us, and it's been really fun, kind of bringing this to the attention of the students. One of the things that we did pretty regularly is we'll have design meetings with the teams, and very often we'll find a cross section of a historic turbopump, and we'll go through that, and I'll get the students speculating on what different features are, what's actually going on here, and we'll talk about some of that. And I think one of the things that I've been the most proud of is as we've gone through that, we're at the point now where I can like throw a cross section from some experimental turbo pump or some a student turbo pump at our students, and they'll look at that, and I can ask them, so what do you see here that maybe is cause for concern? And they've been nailing it, right? They really are understanding turbo pumps as systems increasingly, so that's been very cool to see.
And you kind of having that holistic mindset when building something is exactly the reason why we have an integrated system and why we wanted to provide
Yeah,
a tool like that for, people like yourselves, engineers like yourselves, to have that, holistic view of turbo machinery and thermal fluid systems. So
yeah.
it's great that those mindsets marry up there. My next question for you is essentially, you know, with this being such a complex project and a lot of things you're trying to accomplish in turbo machinery are complex. There's going to be snags along the way. There's going to be issues along the way. And just wondering what those have been like so far, and maybe how AxSTREAM has helped with those, if at all.
Yeah, absolutely. I mean, one of the biggest, of course, is the whole supply chain piece when you're trying to actually build real hardware. And so as part of the project, we've been really trying to do that, like develop an entire supply chain. And there are always going to be key components that are probably going to be long lead time and rather expensive. Bearings for liquid oxygen pumps are not really off the shelf items, and so if you want your machine to last for more than 10 seconds, then it takes some work to figure out how you're going to do that. So those have been obviously challenges, but we've I think been pretty successful at pulling together the right group of suppliers to do it. On our pump, because it's so small, that's been very much a double-edged sword, because on the one hand, the power required to drive it is low enough that we can actually achieve that with relatively affordable off the shelf brushless DC electric motors, which is a huge help when you're actually testing hardware. Even if you're ultimately trying to build a turbo pump, having the ability to run your machine over a range of speeds and inlet and discharge conditions allows you to map your pump in a way that is much harder to do if you're driving it with a turbine. So the size has been helpful that way, but it creates some really big challenges. Like I remember the first designs we were getting from preliminary design in AxSTREAM for our kerosene impeller had a minimum blade height at the impeller exit of like 0.8 millimeters. And so looking at that, it's like, okay, there's no way we're going to be able to produce that with anything like the kind of tolerances we would need for this to be workable. Um, so it required the students to do a bit more of a deep dive into what these, 100 different parameters that relate to impeller design actually mean, and then look at how we can go and try to tweak this to produce something that hopefully still has relatively good efficiency, but also is producible, um, and doesn't end up being like all boundary layer in the flow paths and things. The other thing that was a real challenge is for a pump this small, an open-faced impeller isn't really an option because tip losses are going to be absolutely insane. So we decided very early on that we were probably going to need to do a shrouded impeller. And that creates some manufacturing challenges if you're trying to do one that is this small, because you can't easily get in to machine or clean up those surfaces under the shroud. So this has been one of those areas where there's a strong interplay with the hydrodynamic design of the impeller, as well as the manufacturing side. So AxSTREAM has made it really easy for us to play and explore that design space in a way that you really never could have done.
Mhm. And going from here, I know off the top you kind of mentioned just the growth of Launch Canada, of rocketry teams, student rocketry teams
Yeah.
in Canada. I guess my question to you is where do we go from here? I know there's been a ton of growth in the last couple of years, but separate from the Turbopump project, just where do you see Launch Canada going from here in terms of the aerospace and rocketry growth in
Mhm.
Canada? Where do you see it going from here?
Yeah, so one of the things that we really tried to do with Launch Canada from day one is not be too prescriptive to the students in, what kinds of projects we do and don't allow, what the requirements are, because ultimately there's almost nothing more multidisciplinary than a rocket. So the rocket itself might be that like big compelling ambitious project that draws people in, but once they start it they realize that no, you've got 100 different sub projects here at least. And so there's a lot of scope for them to kind of choose your own adventure and focus on whatever aspects of that technology are most interesting. So you might have, one team that's really heavy on the electrical engineers, so they might just buy a big off the shelf solid rocket motor, but really go to town developing their own avionics and telemetry for the rocket, or a really cool payload or something like that. Other teams want to get into the propulsion side of things. We're increasingly seeing teams interested in exploring active controls and stabilization. So I think the coolest thing is just the scope that this presents. And our whole philosophy has been, let the students tell us what areas of the technology really excite them and motivate them and make them want to spend all their free time learning. And then we will figure out what particular mountains we need to move to support them in doing that. Um, this year at Launch Canada, we actually had the first ever civilian liquid propellant rocket launch in Canada. That was the team from the University of Waterloo. And not only that was that a cool historic first that really raised the bar for Canadian student rocketry. Um, there was about a year or two of legwork that went on behind the scenes between myself and Transport Canada to make it even possible to launch something like that here. So this is the kind of thing that we do on the regular. We'll see what the students want to do, and we'll figure out what we have to do to connect them with the resources and support that they need to be safe and successful doing it. So I think that even looking ahead to next year, we've got teams pushing for higher altitudes. We're definitely going to see more liquid rockets. I could see turbopump fed launch at some point in the not too distant future as well. And I think the most exciting thing is, as these students graduate, we're getting actually a good number of them coming back and joining us as volunteers to help pay it forward and support the next generation. So that's been really cool. We're really building this whole pool of expertise that just keeps growing. But we also have students who are going on into industry. We've got, like I mentioned, a number of startup companies that are being very heavily supplied with talent from Launch Canada. And we've got students who are even going to work at companies like SpaceX and Rocket Lab and Rocket Factory Augsburg and others. So we're really aiming to produce some of the top up and coming aerospace talent in the world, and I think we're succeeding at that. And because rockets are so multidisciplinary, some of our biggest sponsors at Launch Canada have been companies like Pratt and Whitney and MDA Space, neither of whom actually build rockets. But of course, these are such multidisciplinary problems that there's a tremendous amount of crossover. And so a lot of the more traditional aerospace companies have been major beneficiaries of this talent as well. So I think the biggest thing that I want students to come away from this experience is, knowing that they don't need to feel that any area of this technology is out of their reach. If they watched the recent Falcon Super Heavy landing back on chopsticks on the launch pad and thought, my gosh, that is like the craziest thing I've ever seen. I want to know more about the technology that does that. We want to do what we can to create pathways for them to explore that in whatever way we can manage it. So that's really